Hello, Science 30, and welcome to the next part of the story of the electromagnetic spectrum, so radiation spectrum. Let's start talking about the history and discoveries that occurred once we started understanding. So, we're going to start our story off with Sir Isaac Newton when he discovered visible light in 1666. Now, he used a crystal and white light shone through, and then he saw the spectrum. So he was kind of like, oh, there's more than just light in light. Now, Sir Isaac Newton is known for a lot of great discoveries and a lot of great things that happen. But I always find it interesting his story about the apple falling on his head and him going, Eureka, I got it. And he then discovered gravity is actually a very different story. Um, he actually discovered gravity because when he went home, back to where he lived after being in the city, he was sent home essentially because the bubonic plague was running rampant where he was. So they sent him home to be kind of safe from bubonic plague. And while he was there, he was staring at the apple tree and an apple fell. And he was like, ah, and then he kind of thought of it. So still apples involved, but none of that falling on his head. So you have to think about it. 200 years later, or a little less than 200 years later, is when we started to discover other parts of the spectrum. So visible light was something that was discovered quite quickly, but it wasn't until the 1800s that Sir William Herschel discovered infrared. Now, how he did that was he essentially took a bunch of thermometers and laid them out in the different spectrums of light. So like blue, green, all that stuff. So when visible light came through and broke into the spectrum, he laid a bunch of thermometers down. And then what he did is he laid another thermometer down beside the red wavelengths. And he set it there and he left it there. And then he measured the temperatures that he was seeing given off by these different shades of the spectrum. And what he discovered was that from blue to red, it got warmer. But just outside of red, where there was no visible light, that was actually the hottest out of all of them. And he was like, oh, this is interesting. And that's how he kind of discovered infrared light. Shortly after that, in 1801, Johann Wilhelm discovered UV radiation. And then again, it took a little bit of time. And we then started to see some more discoveries. So in 1880 and in 1887, Heinrich Hertz, we now name stuff after him, the Hertz, okay, discovered radio waves and microwaves. All right, so he was a very, very smart man, and he originally was studying radio waves or electromagnetic stuff when he was young, like about age 22. He was studying it, but it was too difficult, so he decided to give it up and do his doctorate and do other things, and then he revisited it once he started to lecture at the university he was working at. And from there, he discovered radio waves and then microwaves. Wilhelm Röntgen, I probably said that wrong, but he discovered X-rays. And what I love about it is he's an example of accidental science. When science happens and you're like, whoops, oh, hey, I discovered something. He was actually trying to shoot different things through cathode rays, and he had it covered up. And he realized there was this light being emitted, and then there was pictures being made, and he was like, what is happening? And he didn't know how this was happening. He didn't know what these wavelengths were that were creating this light. So because he didn't know it, he called them X, meaning unknown. And we now refer to them as X-rays because that's how they got their name. And then lastly but not least, in the 1900s, Paul Villard discovered gamma rays. Now, gamma rays are kind of cool because they are used a lot to study the cosmos. And he discovered them, and he actually was looking at X-rays in the process of discovering them and realized that there was another set of rays that was able to penetrate even further. He was working with radium at the time. And a lot of scientists talk about X-rays and gamma rays quite closely because on the spectrum, they're so close together that hard X-rays, so ones that are getting more and more smaller in their wavelength, cross over a lot with gamma rays. So there's a lot of crossover there. So these are the guys that helped us understand the spectrum and discovered what was on it. So now let's talk about how we actually see EMR through traveling through the Earth's atmosphere. So first we have to kind of talk about what is the Earth's atmosphere and all that stuff. So essentially the Earth's atmosphere is the layer outside of the Earth that absorbs UV light. Okay, it also absorbs visible light and infrared light. So when the sun shines down, which has UV light, okay, and it enters into the Earth's atmosphere, we don't actually get a ton of the actual sun hitting us. It's actually a very, very small amount. A lot of it is absorbed, bounced back off due to our atmosphere, absorbed in our atmosphere, or then hits the ocean and absorbs there. Very little light actually hits ground. So when you are talking about how the Earth's atmosphere absorbs it, we are talking about water vapor, carbon dioxide, and different ozone gases that are within our atmosphere that are trapping those different UV radiations. So that's why there's a lot of focus on making sure that our ozone layer is safe, because when we put different types of pollutants in the air, CFCs and stuff like that, we actually deplete and eat away at what we call our ozone. As we do that, more and more light from the sun is able to enter into our atmosphere, and rather than being bounced back or absorbed, it's actually making its way down to our planet, which is causing us to warm up. Then, because it's getting through, rather than carbon dioxide reflecting it and moving it back away from planet Earth, now that it's on planet Earth, it's bouncing, the heat is bouncing up back to the atmosphere, and carbon dioxide is actually trapping that heat on our Earth. So that's how the ozone layer and global warming kind of work together. And how it's happening is because UV, visible and infrared radiation, can pass through without an ozone. With the ozone, with carbon dioxide and water vapor on the outside, it can bounce off or be absorbed. So as we know, EMR is something that, like X-rays, for example, we know it's helped us a lot. So we're going to go through and talk about some pretty big things that have happened because of different discoveries. So the different EMRs, all the things that we can do with them. So if you look in the medical field, there is a lot, okay? So diagnostics, so ways that we can actually look and diagnose what people have, that's diagnostic procedures. There is a lot that are used. So CT scans use X-rays so we can scan and look at different parts of the bodies. Ultrasounds use sound waves. So they're not technically EMR, but we're still using a wave of some point. X-rays and mammograms. So X-rays can check for broken bones, misplaced joints, all that stuff. Mammograms check breast tissue to check for cancer. MRIs use radio waves and magnets, and the idea is, again, to get a clear picture of what's going on in your body. I've had the pleasure of having MRIs both on my neck and on my knees, and it's a big machine that does this whirry sound, and essentially afterwards you get a really clear picture of what's going on inside someone's head, or in my case, my knee. PET scans are radioactive substance injected into your body, and they give off gamma rays. So I have also had one of those where they injected a dye into my body and then put me under a scanner and were looking for issues. They were trying to find what was happening in my joints. So it was really interesting being injected with this dye. It was a very different experience. Angiograms, again, are injecting some sort of radioactive dye using an X-ray, and we're trying to look for the view of blood vessels to the heart. Angiograms are specifically designed because we want to make sure that the blood vessels on the outside of that heart, the coronary system, are working well, and all the vessels coming in are working well, because otherwise you could suffer a heart attack. PEMF, or pulsed electromagnetic field stimulation, okay, is really interesting because they use it for a variety of different things. It's directing radio waves at damaged or injured areas of the patient's body. And the idea is that it wants to start to help speed up the healing process of those tissues. Okay, so they use it in bone repair, they use it in nerve stimulation and tissue regeneration. They use it a lot in post-op, so after operations, to help really speed up that healing process for people that are suffering from, like, they're trying to recover from an injury and then they get the operation. But another interesting thing that they've started using PEMF for is to help deal with depression. So sending radio waves at the areas and trying to essentially target the brain and help with a healing process, or help regenerate some areas to get some hormones flowing. Radiation oncology is another one that we can talk about. It is essentially looking at radiation to help deal with different things like cancer. So looking for ways to deal with, like, tracking and monitoring cancer. So brachytherapy is when you put in small metal implants near a tumor, and then what you do is that tumor is then shrunk by the radioactive materials from the small metal implants. So the idea is it's a lot more precise. You can then shrink that a little bit better. Linear accelerators and gamma stereostatic radiosurgery. Again, these are just sending high doses. Well, the x-rays, you know what x-rays are, but the gamma stereostatic radiosurgery is essentially a high dose of radiation sent to the specific areas in the head or the neck to target these tumors. You can also do it to the liver and the lungs. You're precise. They call it precise because when they do this to the head or the neck, it's a one shot kind of thing. They only do it once. But if you're doing it for the liver and the lungs, you're going to do it 3 to 5 times approximately. So communication purposes, we use EMR for television, radio waves, cell phones, Bluetooth, Wi-Fi, GPS systems, AirDrop. All of these use some sort of radio wave to help us communicate, right? So if you think about using your cell phone, GPS, it sends a signal up into the sky, triangulates with a couple of other GPSs, sends it back to your phone, and you know where you are, okay? Cell phones use radio waves, television, radio, lots and lots of different things communicate using our radio waves. In industrial purposes, we have things like gauging devices, X-ray fluorescent analyzers, gas chromatographs, sorry. So these gauging devices are essentially used to monitor liquids, flows of liquids, okay? And they're essentially looking for radioactive materials that release gamma rays, sorry. So when you're using an X-ray fluorescence analyzer, they're used to determine the makeup of an item. So they're trying to figure out what's inside by using X-rays. Gas chromatographs are used to look for the purity of a substance. So they're checking the different gases to make sure you have the correct substance, so you're not going to have any breakdowns or blow-ups. It's also used in logging as well, because we want to sometimes determine mineral, rocks, gas, and other oils that we're drilling for. We want to use different types of EMR wavelengths, radioactive materials, to look for what's in those types of soils. We also have non-destructive testing, which look at pipes so that they can check to see if there's any sort of irregularities. They usually use X-ray machines to do that. And then sterilization is another big one. Is when you're sterilizing products, you're going to often use UV radiation, and you're going to, or some sort of gamma emitting radiation, especially at a higher level. And it's going to then be part of like something like hospitals or post offices. They use these processes to irradiate and sterilize certain components. And then power generation uses also radiation sources to create electricity, thermal power, and all that. But it also powers spacecraft, satellites, lots of different stuff, weather stations, all those kinds of things. So when we're talking about the environment, okay, we have learned that there's a couple ways we can use EMR to solve some problems in the environment. UV radiation has been known to help break down plastics because we know plastics are not biodegradable. So when you recycle them, they use UV radiation to break them down to reuse. We also know that we want to be able to sterilize certain things because without it, we can get microorganisms that make us sick. So sterilizing food using UV radiation, or even sterilizing the water that we put back into the river, is really important. Okay. Plants use UV radiation for photosynthesis. Obviously, we think that is one of the most important processes of life. Weather, water, and climate scientists really rely heavily on radio waves, satellites, and all that stuff to transmit data so they can give you information about what's happening into our weather, what's going on in the ocean when there's like such a hurricane or anything like that. Conservation biologists use environmental biology. In environmental biology, they use a lot of different things. GPS, satellite tracking, especially when they're tagging animals and then wanting to study them for long periods of time, they need radio waves to do that. And then again, whether we use any sort of communication device to conduct any research or communicate the things that we find in the world, this is all using some sort of spectrum of the EMR. So how has it helped us understand the world around us? And this is the part that I find extremely interesting, you guys. So back in the day, we just had a telescope. We looked through the telescope, boom, there's the universe. That's all we had. Then scientists realized that telescopes could be made better, and we could see farther and further into the sky by using things like mirrors and lenses to collect waves, focus them, and then add in different parts of EMR, and all of a sudden you can see vast parts of the universe. So visible light coming in from stars allows us to see certain things, celestial objects, but by using things like radio waves and infrared and X-ray and gamma rays, we're able to put all this information in and look past what we can normally see further and further into space, because what it does is it collects these waves by bouncing them off different things, associating them with color, and then we can create a picture by basing things off of color. So blue is a light, is cold, red is hot. So you can see like, oh, if red's hot, maybe there's something there like a star. So they start collecting all this information and then create a visual for us based on all of these different ways that we can see radio waves bouncing off and gamma rays bouncing off and all that stuff. So it's also helped us with the theories of the atom. So Dalton back in the day proposed that you couldn't divide the atom any further. Thomson said, well, yeah, you technically can because there's things called electrons. And then Rutherford said, hey, you know what? There's actually something called a nucleus, and it probably has something called a proton. Bohr later on came along and said, you know what? So it's not just a sphere. It's not just a circle like the other people thought. It's actually something small in the middle with all these different orbiting electrons fixed around it, like going round and round circles. That was in 1913. In 1926, they finally said, you know what? Atoms are made up of electrons, protons, and neutrons. In these electrons have orbital space around the nucleus, but they're not perfect. They can move around and they can go in different directions, and it's very cool. So when they started theorizing about the atom and what it looked like, they often compared and confused this phenomenon of the atom with the electromagnetic spectrum, because Thomson was using a cathode ray, and what he was recognizing was when he was using this cathode ray, it later helped him discover electrons, that it traveled in straight lines, and it also had similar chemical reactions to the electromagnetic spectrum. What he observed was differences as electrons were not deflecting within a magnetic field. So then he was trying to figure out, like, what's going on if I have this a negative thing and it's going straight through? How is that possible? It should be bending because it's negative and bending towards a positive. So he deduced that electrons are actually different than the electromagnetic spectrum just because of all these differences. So essentially he was just saying, hey, look, electrons are not part of this, and so then theorized how the atom was actually functioning. So that's it, ladies and gentlemen, and I hope that you were able to get all of this into your notes, and we will talk soon.